When we have a balanced equation, we know the ratios that two or more different reactants will need to react in order to form a certain amount of product. In the laboratory, the amounts that we start with, however, are usually in grams. And so the idea of stoichiometry is that we're going to be able to work with the amount of substance that's involved in the chemical reaction, both from a reactant standpoint and also a product standpoint. Now, the balanced equation and the coefficients in that balanced equation give us the ratio of the number of particles that are reacting with one another. But each particle has its own unique mass, so that we need to be able to relate the masses that we measure in the laboratory to the ratio of particles that we get from the balanced equation. And there's 4 steps to being able to undertake one of these stoichiometry problems, which, to make a brief analogy, if you have 20 slices of bread in a loaf and you are trying to determine how many sandwiches you can make with that loaf of bread, assuming that we're making a typical sandwich which consists of 2 pieces of bread, 20 slices in a loaf will be enough to make 10 sandwiches. Using that same basic idea, that's what we're going to be looking at with stoichiometry in chemical reactions. For a given amount of reactant, how much product can we make? And it's not really limited to just reactants to products, but no matter which direction we're going, no matter what we're starting with, what we're ending with, we're going to be completing a mass-mass conversion. Mass of a starting material to mass of a final material. 4 steps are required. First, we need to have a balanced equation. Without this, we are not going to be able to get the proper amount for our final mass. In a mass-mass problem, you'll be given a mass of starting material that you are given. And the first step is to convert that from grams into our unit for a number of particles, which is the mole. So to convert from grams to moles, we use molar mass. Once we're in moles, now we can utilize that balanced equation and the coefficients in the balanced equation to determine the ratio of our starting material to our final material. And then finally, once we have converted to moles of our final material, then we can use its molar mass to convert it back to grams and the final answer that we seek out. To take these 4 steps and put them in a graphical formation, remember, we are always going to start these mass-mass problems being given grams of a starting material. Now, that starting material could be either a reactant or it could be a product, depending on the perspective of the problem that you are trying to solve. But the first step is to convert that mass of your starting material into a quantity of how many particles that you have of that material. And the quantity that we like to use is the counting unit, the mole. So to convert from grams of your starting material to moles of your starting material, we need to use the molar mass of that starting material. Molar mass being grams per 1 mole of that material. That value is obtained by using the chemical formula for that starting material and the masses from the periodic table. Once we've converted the amount of starting material we have into moles, now we use that recipe, that balanced equation, to determine the relationship between how many moles of starting material do we have to how many moles of final material. What is that numerical ratio? And so to complete the conversion from moles of starting material to moles of final material, we need to determine the mole ratio of those 2 substances. And that mole ratio is determined by looking at the coefficients from the balanced equation. And that's why having a balanced equation first is so vitally important. The setup of that mole ratio, as with all of these conversion factors, is determined by what units do you want to factor out and what units do you want to continue on until the next step. In this case, the starting material is going to be on the bottom and the moles of final material will be on the top of the conversion factor. Finally, now that we know how much of our final material in terms of particles we have or we will obtain, we want to convert it into units of grams. We want to convert it to mass. So to convert from moles to grams, once again, we are going to use molar mass. This time, however, the molar mass that we plug in for the grams portion of the conversion factor will be for that final material as determined by its chemical formula. And it should also be noted that the setup of the molar mass conversion factor, where the grams go, where the moles go, is going to be opposite what it was in the first step. Because in the first step we were trying to cancel out grams. Here in the last step we are trying to end up with grams. So to summarize this in an equation type setup, we will always start with our original amount of material that's given to us, our starting material, in grams. The first step then is to use the molar mass of the starting material. Seen here in blue, this will be the setup. We want the grams to cancel out, so we place it in the denominator. And molar mass is always in terms of 1 mole of starting material, so that goes in the numerator. Next is to go from MOSM to MOFM, moles of starting material to moles of final material. And again, the numbers that we use in this ratio will come directly from the coefficients. So when you look at your balanced equation, whatever your starting material is, whatever coefficient goes in front of its formula, that's the number that goes in your denominator. Whatever the coefficient is for the final material's formula, that number goes in the numerator. Finally, to go from moles of final material to grams of final material, we need to use the molar mass, seen in red here. And again, note that the grams this time are on top in the numerator, whereas in the first step, highlighted in blue, it was in the denominator. The setup of your conversion factors in a factor label problem is driven entirely by the ability to factor out the labels that you don't want, that you are trying to get away from, and the ones that you do want to end up with end up being the units that are left over. When we take a look at a stoichiometry problem, we need to first determine what it is that we're being given to start with and what it is that we're being asked to find. And the other thing that we need is to have a balanced equation. Sometimes that balanced equation will be given, as it is here. Other times we may need to use what we know about the reactants, about the reaction type, what we can predict, and also predict the products that would be formed and then balance it. In this case, the balanced equation is given to us. And before we get started, a good practice is to take what you know from the problem and what you're being asked to find and write those things above the balanced equation. So that way you have your most important information all in one spot. So you would write the 9.90 grams above the CuCl, and you put a question mark above the Cu2S so that you know exactly where you're starting and where you're trying to get to formula-wise. First step in the calculation is to begin with the mass that you're given, which is 9.90 grams of copper 1 chloride. First step is to convert from grams of starting material, the starting material here is the copper 1 chloride, and convert that to moles. So we need the molar mass. Using the periodic table, molar mass of copper 1 chloride is 99.0 grams. The grams will cancel, leaving us with moles of our starting material, copper 1 chloride. The next step is to use our mole ratio. In the mole ratio step, the final material is always on top and the starting material is on the bottom. So the moles CuCl will be in the denominator. The numbers come from the balanced equation coefficients. CuCl has a coefficient of 2, so we'll have 2 moles CuCl on the bottom of this next conversion. And the Cu2S has a coefficient of 1, thus giving us 1 mole of copper 1 sulfide in the numerator. Moles of the copper 1 chloride starting material cancel out. And now we're at moles of final material. Final step is to convert to grams of final material utilizing the molar mass of copper 1 sulfide. And again, using the periodic table, we should calculate 159 grams with proper sig figs. And now that we're in the units for the substance that we are asked to find, now we're ready to do our calculation. So we multiply all our numerator terms together, likewise for the denominators, and then do the division. If we consolidate numerators and denominators, we get 1,574.1 divided by 198 grams of Cu2S. And in simplifying that and using proper sig figs, we should come up with an answer of 7.95 grams copper 1 sulfide. in this example, we're asked how many grams of calcium hydroxide would be needed in order to completely use up a 10-gram sample of phosphoric acid. In this case, we are not provided with a balanced equation, so we need to take the fact that we are reacting calcium hydroxide and phosphoric acid, two compounds. And if we think about our different reaction types, this would suggest a double displacement reaction. In fact, if you know anything about acid-base reactions, hydroxides are typically Arrhenius bases, and phosphoric acid is an acid. Acid-base reactions are double displacement reactions. So we're going to swap the cations to predict the products, which would give us calcium phosphate and hydrogen hydroxide, or water. And when we balance that equation, then we would come up with the following equation that you see here. Writing in what we have so that we know where we're starting and where we're going to, we have 10 grams of H3PO4. So you should write the 10 grams above that formula. And our question mark this time goes above the CaOH2, parentheses 2. And so you'll note that we are working exclusively on the reactant side of the equation, which may lead you to ask, well, why do we need to balance the equation if we don't need any of the products? And the reason is because at that mole ratio step, we need to have the correct coefficients. And the only way we can get the correct coefficients is if we have the entire equation, reactants and products. So the balanced equation really is necessary. If we start our calculation with the 10 grams of phosphoric acid, we need to first convert to moles with its molar mass. The grams go on the bottom. Next is the mole ratio step. The final material, calcium hydroxide, will go on top. There are 3 moles of calcium hydroxide, based on the coefficient of 3 in the equation, over the 2 moles of phosphoric acid. And the last step is to convert to grams of our final product, and we need the molar mass of calcium hydroxide for that. Now that we're in the units of the substance we were asked to find, we can simplify our numbers, consolidate the numerators, consolidate the denominators, and then do the division. And when we solve for a final answer, we should have 3 significant figures in our final answer of 11.3 grams calcium hydroxide.